when you're finished, just flick it back again to turn it off.
Brilliant, thanks. Cheers.
That's all.
Ready?
Good.
Okay, welcome to the final day of this workshop. I want to welcome Martin Liebeck to give his second talk on the subgroup structure of almost simple groups.
Oh, goodness, I've destroyed it. Where's it gone? Apologies. The chairman will deal with Thanks, Rob. Right, good morning. So this second talk I'm going to focus on exceptional groups of Lie type. So this will be, I'll give you some as up-to-date results as I can on maximal subgroups of exceptional groups of Lie type. So generally I'll call such a group G of Q, and that's just a group like E8 of Q or E7 of Q. Okay, the familiar list of exceptional groups of Lie type. Okay, so to discuss this, we need to move into the world of algebraic groups and have the usual setup of regarding G of Q as the fixed points of a Frobenius endomorphism of an algebraic group. So here's the setup and the notation I want to adopt. So let's see, we'll take a algebraically closed field of characteristic P. Of course, Q will be a power of P in our setup. G I will denote by a simple algebraic group of exceptional type, so over K of exceptional type. So one of the types E8, E7, E6, F4, G2. Right, and then we want the root system and root groups and all the usual stuff. So T will be a maximal torus of G, and the corresponding root system capital Phi, and then we have corresponding root groups, which I think I'm going to call U alpha. So root groups what else do I want? Oh yes, I want a base for the root system. I'm not sure if I need notation, but let's have alpha 1 up to alpha L, and then I'll want to refer to the extended Dynkin diagram. So the extended Dynkin diagram, where we join the negative of the highest root. So for example, I think I'm going to do lots of examples with E8. So the extended diagram of E8 is when you just take the, how many is that? 7, right? There's the E8 diagram, and the extending node is at that end. Right, any other notation? Oh yes, and finally we'll have F will be a Frobenius endomorphism of G, and the fixed point group will be our group G of Q. So that's the setup, all very standard. Right. Okay, and the aim is, in this case, unlike in alternating or classical groups, is to find all the maximal subgroups up to conjugacy. Every single last one of them. So to find all maximal subgroups of G of Q and all the related almost simple groups. Okay. Okay, I won't write that down. Right, so, well, there's lots of stuff to tell you about this. It turns out that a very fruitful way of studying the finite groups, as in representation theory and all sorts of other theories, is to look at subgroups of the algebraic groups and then pass down to the finite groups via this Frobenius endomorphism. I guess we'll have section 1. We'll look at subgroups of the algebraic groups. And then hopefully we can pass down to the finite groups using this theory here. So, okay, and we're not going to look at finite subgroups of the algebraic groups. So we'll look at positive dimensional subgroups of the algebraic group. Okay, so there's a complete story to tell you here. So examples of maximal subgroups of positive dimensions. These are going to be maximal. Of course, we've got the parabolic subgroups. So just remind you, if we take our E8 diagram and we just circle some subset of the nodes, let's call that subset I, then Pi is the subgroup generated by our maximal torus, and all the root groups for positive roots and also the negative roots in I. So that will be a parabolic subgroup. These are very well understood. Everybody knows about them. We have a unipotent radical and then a Levy factor, and the semi-simple part of the Levy factor is just the group corresponding to the subset I we've picked out. So in this case it would be A4, A2. Right, so parabolic subgroups, they're very well understood. Let's pick out another very well understood class of subgroups. So we call these subsystem subgroups. And here we just pick a subsystem of the root system and take the group generated by the corresponding root groups. How can I write that down? So let, say, sigma be a subsystem of our root system phi. So that means that it's closed under sums in the following sense. So if we have two roots in sigma and the sum of those two roots happens to be a root, then the sum is in sigma. So usually called a closed subsystem. And then given a subsystem, we can define a subsystem subgroup just by doing what I said. Take the group generated by all the roots in the subsystem. So that's a very fruitful source of natural subgroups of our algebraic group G. I want to write down a collection of subsystem subgroups for E8. So there's a famous algorithm for generating all of the subsystem subgroups up to conjugacy. So you write down the extended diagram. very bad at counting up to 7. Right. Right, there's our extended diagram. So this famous Borel-de Siebenthal algorithm says to get all the subsystems, just take the extended diagram, cross out some nodes. Let's cross out that one. Well, I'll just say what it is, and then I'll do some crossing out. Cross out some nodes. What you've got left is a subsystem. And then take the extended diagram of what you've got left, cross out some nodes, and just repeat this process. And that algorithm will generate all the subsystems. So of course, you'll get some which are conjugate to others, but you'll get all of them by that process. So I want to pick out the maximal ones, maximal positive dimensional subsystem subgroups. So I'm going to place my finger over various nodes. So if I place my finger over that one, I get A1, E7. So I'm just going to write down a list. If I place my finger over this one, I get, you can see A2, E6. I could place my finger over the next one and get A3, D5, but it turns out that doesn't give you a maximal subgroup. That's contained in this D8, in fact. So, but the next one gives us, well, this one, A4, A4. Then I don't get any more maximal ones until I go over here. I get D8, and then if I do that one, I get A8. So there's some great big juicy subgroups of E8. I'm actually going to write down a few more that are not maximal as connected subgroups, but turn out to give you maximal subgroups of positive dimension. So also within the D8, we've got D4, D4. That's not, of course, that's not maximal among connected subgroups, but it turns out if you take its normalizer, you get a triality, you get a S3 of graph automorphisms on top of it, which does not normalize the D8. So this, in fact, leads to a positive, a maximal subgroup of positive dimension. Similarly, within the A2, E6, I can get an A2, and then if you do this algorithm with the extended diagram of E6, you can get an A2 cubed. So we get A2 to the 4th, and then by repeating the algorithm many times, you can get A1 to the 8th. So I think that's my full list that's going to lead to maximal subgroups of positive dimension. Yes. So let's call this list star. And so here's the theorem. So theorem 1. So this has quite a bit of history, and so this is the classification of the maximal positive dimensional subgroups of exceptional algebraic groups. In characteristic 0, of course, there's such a question, and that was solved in famous work of Dinkin. This was taken up in positive characteristic by Gary Seitz, who proved it excluding excluding some small characteristics, and then Gary and I finished it off in arbitrary characteristic. So, and what does it say? So let me just state it for E8, just to avoid writing too many lists of things. So the maximal positive dimensional subgroups of the algebraic group E8 are, it's kind of quite a surprisingly short list. So we've got parabolics. Of course, we have to have maximal parabolics, where we just cross off one node from the Dinkin diagram to get our set I. Subsystem groups. So this is the list, actually. So if you take the normalizers of these subsystem subgroups, that's the full list of maximal subsystem groups. As I said, they're not all, these ones here are not maximal connected, but their normalizers are maximal. And then we mustn't forget the subsystem subgroup corresponding to the empty subsystem. So that's just the maximal torus. So normalizer of T. That's a maximal subgroup of positive dimension. And apart from this, just a few other classes. Just 6 or 7 other classes. Anyway, a finite number. I can't remember the list. So, say a few further classes. I'll write down. So these are not quite so obvious to see within E8. So let's say M is our maximal subgroup of positive dimension, then its connected component is, well, there's a great big subgroup, G2 cross F4 inside E8. It's very well known. Inside that is a G2, and in the F4 there's a G2A1, and it happens that the two G2s are swapped within E8, so that's the normalizer of that is maximal. What else have we got? We've got an A1, A2, a B2, and then some classes of A1s. There's actually 4 conjugacy classes of these A1s. Anyway, so a finite number of classes of maximal subgroups of positive dimension, and that's the case in all simple algebraic groups. But okay, so that's the story for the algebraic groups, and now we aim to use this to get a kind of corresponding result for the finite groups. So, well, aim. Here's our aim, corresponding for max subgroups of let's call them H of G of Q. So what kind of flavor would we here's the aim. The flavor should be either H is just kind of the fixed points under the Frobenius of one of these nice algebraic subgroups. So let's say H equals the fixed points of one of those lists. So M is like an F stable positive dimensional maximal subgroup, as in our theorem. Yes, good, I called it. Okay, so that's going to be a list of mainly maximal subgroups of G of Q. We mustn't forget these subgroups, which only occur for finite, in the finite case. Just you take the same group like E8 over a subfield. That's going to be a maximal subgroup if the subfield has prime index. So those will occur. And then apart from that, we expect some maximal subgroups, but they'll kind of be sporadic. They'll be I don't mean sporadic, I mean small, piddly subgroups. So as a small list of exceptions. We already see in PSL2 this kind of theorem holds, right? We have parabolics and dihedral subgroups, then we have subfield subgroups in PSL2, and then we have like A4, A5, and S4, right? So that kind of small list of exceptions. And we hope to, but of course we want to find all these groups. Let me call that L for the list of exceptions. And as I go along, I'll tell you some results, and we'll see what goes into this list of exceptions. So that's the aim. And as we'll see, this aim has been pretty much realized except for the two largest groups, E7 and E8, where there's still work to do. Right, so the first step I want to tell you about is a kind of Ashbacher type theorem for exceptional groups. So let's have another section, shall we? So let's say this is a reduction theorem, like Ashbacher sort of reduces the study of maximal subgroups of classical groups to the study of simple groups in some sense. So a similar kind of reduction theorem applies for exceptional groups. So let me tell you what it says. Right. Okay, so okay, so I'm just going to state it for E8 again, just to save writing too many lists of things. So take a maximal subgroup of E8 of Q, then no, one of the following holds. One of. Okay, so let's start off with the so I don't forget it, that H is almost simple. That's going to be our Ashbacher type dustbin where we have to do further study. But apart from that, we can say exactly what the possibilities are. So the second one is just our algebraic subgroups. H is the fixed points of a positive dimensional subgroup, and one can easily work out all those possibilities. It's just a matter of applying Lang's theorem, essentially. What else do we have? I seem to have forgotten to write down the subfield subgroup, so let me write those down. Right, so apart from this, we get two little groups to put in our list L, and they're, no, three little groups, and they're all rather beautiful and unexpected. So here we have two very amazing local subgroups. So let's say E. E is elementary abelian, so we call these exotic local subgroups. And the possibilities are, there's a famous subgroup here, it's the normalized, here E is 2 to the 5, elementary abelian, and there's an extension of 2 to the 5 by a 2 to the 10 SL5 2, and then there's also a 5 local subgroup, 5 cubed SL3 5. So those, there's one conjugacy class of each of these. Those sit inside E8 of Q for appropriate values of Q. And then there's one more. I think I can squeeze. If you don't mind, I'll squeeze the fifth one. This is even more amazing. So the last group here is not almost simple, but it's a product of an alternating group. All right, alt 5 to, because A5 means something for algebraic groups. So alt 5 plus alt 6 with 2 squared on top. So that is. It turns out there is such a subgroup of E8. It is maximal. It was discovered by Borovic. It's just a completely unexpected, amazing subgroup. So we call this the Borovic subgroup. Okay, so that's the reduction theorem. And I wanted to prove something in this talk, so I'm just going to sketch a little bit of the proof of this reduction theorem. So where shall I go? Sorry? In the non-S6 way. Yes, I don't think there's an S6 in that H. Okay, so I'm not going to prove the whole thing. The whole thing was proved in a 40-page paper, but let me just, I can show you one or two little ideas in the proof. So, I left my bit of paper over there. Right, well, we have our finite group H, and so either it's, if we look at a normal subgroup, either it's the normalizer of an elementary abelian subgroup, so it's a local subgroup, or its socle is a product of simple groups. Let's call them F1 up to Ft. Right, and so the local case, of course, we're going to end up with those exotic locals. I'm not going to discuss that. So let me just talk about the non-local case. Well, of course, if T is 1, then we have our almost simple, we have an almost simple group, and we're done. So let's assume T is at least 2. So we have a direct product of at least 2 simple groups in the socle of H. And now comes an ingenious idea that I should have said this theorem was kind of a version of it was proved by Borovic, and then Gary and I proved this more sort of explicit version of it a bit later. So this idea came from Borovic's proof, and it's this observation that if look at the double centralizer of one of these simple groups, say this Fi. So the centralizer of the double centralizer of Fi, the centralizer of the centralizer of Fi, of course that contains Fi. Fi centralizes its centralizer. But the point is that the centralizer of Fi contains all the other Fs. So it's not the identity. So this is definitely a proper subgroup of G. Now G is our algebraic group here. So that's a proper subgroup, and just a very elementary one-line argument tells you that the group generated by all these double centralizers is just their direct product. So H normalizes the direct product of all these double centralizers. So what's the point of all that? So H normalizes, let's say D equals product of all these double centralizers, which, as I said, this is just a commuting product, so this is still a proper subgroup of G. Well, this double centralizer on the face of it could just be a finite group, but if it's infinite, then we've got that H normalizes some group of positive dimension, and then if we take a maximal such group of positive dimension normalized by H, will be in our theorem, the situation of our theorem 1. That'll be very good. So we'd like to force D to be infinite, to have positive dimension. So I claim that either D is infinite, so the connected component is non-trivial. So I don't know. So that leads to H, as I just said, being normalizing a maximal subgroup of positive dimension. That's a good case. Or the other conclusion is that our simple group Fi, or each Fi, is only divisible by the primes 2, 3, and 5. So it's a 2, 3, 5 group. Well, that's pretty good news because there aren't many simple 2, 3, 5 groups. You can even classify them without using the classification. Anyway, so let's see how we prove this. So let's suppose some Fi is not a 2, 3, 5 group, so we can pick a prime larger than 5 dividing it. So suppose there exists, say, X in our simple group Fi of prime order, say R greater than or equal to 7. Right, now we're interested in the double centralizer of Fi. I want to show that's infinite now. So we look at the double centralizer of Fi, and that contains not the centralizer of X, but the center of the centralizer of X. Okay, the center of the centralizer of X centralizes the centralizer of X, which is contained in the, no, which contains the centralizer of Fi. So, not sure if that was very convincing. Anyway, if you do about 30, well, in my case, you need many seconds of thought to convince yourself of this. But anyway, this is certainly correct. So what's the point of saying that? Well, in algebraic groups, there's a whole theory of centralizers of elements. And if you have an element of what's called good prime order, so the bad primes for E8 are 2, 3, and 5. So anything bigger than 5 is a good prime. Then this is an infinite group. So centralizer theory, not at all hard to prove, in fact. Centralizer theory implies the centralizer of an element of good prime order is infinite. Okay, and that's it, right? So that implies if we have an element, if we have a prime bigger than 7 dividing Fi, then this D group is infinite. Okay, so what's the upshot of that? The upshot of that is that we can assume each Fi is a 2, 3, 5 group. What are they? Okay, so assume each Fi is a 2, 3, 5 group. And as I said, you can prove this with or without the classification. There are only 3 such simple groups, alt 5, alt 6, and the unitary group, PSU 42. Okay, well, so there's still some work to do. We want to prove that the socle of H is in fact alt 5 cross alt 6, but you need quite a bit of further argument, so I won't go into that. So further argument. The socle of H turns out to have to be alt 5 cross alt 6, and we get our Borovic subgroup, which it's quite an amazing subgroup to be there. Anyway, so so here, remember I said I'm going to form this list L of small exceptions to the kind of generic maximal subgroup. So obviously the Borovic group goes into the list L, and so do these exotic locals. Okay, so that's the reduction theorem. So now we have to study almost simple subgroups of our exceptional groups. So there's quite a bit to say about those. Maybe I shouldn't have done that. So maybe we'll have a new section. So we're looking for almost simple maximal subgroups of our exceptional groups. Of course, there are two cases, so let's oh, well, now I seem to want to call G our finite group. Oh, sorry, I definitely had some. Oh, I don't want to call it anything. Good. Let's not call it anything. So let's take H will be our maximal subgroup of our exceptional group G of Q. P will be the characteristic. And let's assume H is almost simple. So the socle of H is, let's say, H naught, a non-abelian simple group. Well, there are two obvious cases. H could be a group of Lie type in the characteristic P or not. So, and those are two cases that require completely different methods to study them. So H naught is, let's say, H naught of P to the B, let's say. A group of Lie type in characteristic P. So we call this the generic case. You expect this to lead, you expect there to be very few things to put in your list L from this case. You expect the almost simple groups in the same characteristic just to be fixed point groups of algebraic subgroups. So you expect H to be MF in this case. In case 2, of course, will not, you don't expect that. So H naught of Lie type in characteristic not P, or alternating, or sporadic. Okay. So let me tell you some results about these two cases. Okay, so let's start off with the generic case. There was a result of mine with Gary from, I think, 1998, which at least tells you that provided our P to the B is sufficiently large, and usually sufficiently large is like greater than 9 or something like that, then H is MF. So there are only kind of finitely many unknown cases. So let me state that result, and then I'll tell you some recent rather spectacular progress on. So let's assume that the field over which H0 is defined, p to the b, so we assume it's at greater than 9, as I said, if we're not in the, so let's say if the rank of H0 as the simple group H0 is bigger than 1, so we're not PSL2 or a Suzuki or small regroup, and if we are a Suzuki, a PSL2 or one of those other groups, then it's rather a larger number. It's a number called T of G. The T of G is defined, it's an absolute constant. It's defined in terms of the root system of G, in terms of certain lattices in the root system of G. I think for E8 it's over 1,000, so it's quite large. Anyway, then in this case we get our desired conclusion that H is just an algebraic subgroup. Okay, so that at least has the effect of saying that if the group is, the only unknown groups are less than, have order less than some absolute constant. Well, that was, I mean, obviously that's useful, but there's a lot of work to do to improve this, and nobody really took up the challenge until, very happily for me, David Craven took up the challenge with a vengeance. So he's made a huge amount of progress over the last few years of vastly improving these assumptions for groups up to E6, removing them completely. So let me tell you David's result. So let me just tell you for E8 of Q. So for E8 of Q, as I said, this P to the B is at least 1,000 for the rank 1 groups. So what is David's result in this case? Well, in my notes I've said don't bother mentioning PSL2, so let's exclude. I'm not sure if David's, so exclude H0 equals PSL2 P to the B. But for the rest, he has pretty much got rid of it, just about everything. So then we have our desired conclusion. H is an algebraic subgroup, unless possibly just a few small groups he hasn't got round to dealing with yet. So unless possibly H0 is some PSL3s or PSU3s, so over the field of 3, 4, or 8 elements, or U4 of 2, or Suzuki of 8. So just some small groups in characteristics 2 and 3. Apart from that, he's got rid of everything. Okay, and I think he's working on the PSL2s for E8. Okay, so that's excellent progress on the generic case. What about the non-generic case? There's lots of progress on that as well. Okay, so here our maximal subgroup H0, wherever it is either Lie type in characteristic not P or alternating or sporadic. So again, there was an old result of mine with Gary, I think from 1999, where we gave a list of isomorphism types, certainly not conjugacy classes or anything like that. Isomorphism types of all possible H0s of this form inside exceptional groups of Lie type. So at least you have a, and it's of course it's a finite list, so at least future generations have a great big list to work from. Future generations didn't come along again until Alistair Litterick took up this challenge. So he's written a memoir on reducing this list very significantly. That memoir appeared last year, and then David has taken that a lot further. I think 19 plus, I think we'll give David. 19 plus out of 20, a good mark. Okay, well, it seems a bit miserable to say they excluded lots of possibilities, isn't it? No, but I'm going to state some positive results. So many possibilities excluded. So this was just, there was no maximality assumption in this list of isomorphism types. We just said, so many possibilities excluded under the maximality assumption. So I'm just going to state an example of their result. They have a pretty definitive result for the alternating case, also for lots of other cases, but it's a nice clean result. The alternating case, so let me state that. So, for example, what do Gary and I say about alternating groups? So, alt R, alternating group R, is contained in E8 of Q for some Q, if and only if R is at most 17, I think. So, all the alternating groups, there's some characteristic restrictions sometimes, but right up to 17, they appear somewhere in E8. But Alistair and David have shown that if you have a maximal subgroup with Socle alt R, then hardly anything can happen to it. R is 6 or 7. It's not clear whether alt 6 and alt 7 can actually occur, but anyway, it's a tremendous reduction from the list that Gary and I provided. So let me finally summarize the groups for which everything is known, or practically everything. As I said, it's pretty much all the groups except for E7 and E8. So let's say all maximal subgroups are now known for the exceptional groups of type, well, seems a bit silly to list all the types when it's everything except E7 and E8 of type not. E7, E8, but except for one case in E6, which I'm going to state the result for E6, apart from one possibility in E6. Anyway, that'll become clear. So here's the theorem for E6. So this is something David has recently put on the archive. Not on the archive, on my archive, my email, right? So I guess this is 20 minus maybe. Okay, but of course it builds on all the other theory I've been talking about. But let's be. And it's a complete list for E6 of Q. I thought I'd just. And it's exactly what the kind of thing we were aiming for earlier on with this list L. Okay, so the maximal subgroups of E6 of Q, and okay, he has a similar result for almost simple groups with Sockle E6 of Q, but let's just say E6 of Q are. So first we have the algebraic subgroups, so parabolics and subsystems and a few other classes. Then we have the subfield subgroups, so E6 of Q naught, and also the twisted E6 over a subfield. Has to be the square root of Q in this case. So those are the subfield subgroups. Then we have our list L. What goes into our list L? We have, so remember in E8 we had these exotic local subgroups. Well, there's one of those in E6. It's a 3 local. It's the normalizer of a 3 cubed. So it's of that shape, one exotic local. And then we have a bunch of almost simple subgroups in our list L. Not too many of them. Just 7, I think I've got in my list here. So, okay, so some small, almost simple subgroups. So let me write down the list of these. There's an embedding of M12 in E6 of 5, been known for some time. There's an embedding of J3 in E6 of 4. There's twisted F4 of 2 inside any E6 of P, where P is 1 mod 4. And then there's a few PSL2s, PSL2, 8, 11, 13, and 19 in various PSL2 over a field of P or P squared. And that's it, except I said there's one possibility, so he's still, so David still has to deal with the possibility PSL27 as a maximal subgroup. You think this would be incredibly difficult, right? SL27 is a very tiny group. Can it be a maximal subgroup of E6? Well, I'm sure David will resolve this before too long. Anyway, so I think it's time to stop. Thanks.
Local, are there restrictions on Q to exist?
Yes. Did I write them down? Yes, Q. I should have written it down. Q is a prime congruent to 1 mod 3. That's, sorry, I should have written that down. No, they how does it go? I think the A5 that's right. I think if you take your subsystem A4 and you diagonally embed an alt 5 irreducibly in both factors, I think that's the A5, and then somehow you prove its centralizer is just an alt 6, but it's not. It's all a bit mysterious. Right.